Welcome back to the final session of the inaugural buildingSMART user conference. Thank you very much for your attendance over the last 2 days, and we're at the final session now, which is some openBIM award winners. We have 3 more projects to share with you today from the 2021 buildingSMART Awards. These are exceptional projects, and we have these 3 presentations coming up. If you have any questions, please do submit them in the panel, and we will get to them as best we can. But with that, we'll get started with our first presentation, which is the IfcInfraToolKit from the Technical University of Munich. Over to you.
My name is Sebastian Esser. I'm a PhD student at the Technical University of Munich, or more precisely at the Chair of Computational Modeling and Simulation under the lead of Professor Andre Bormann. I was involved in certain IFC extension projects over the last years as a student. And within that scope, we've developed some prototypes, which is now called the IfcInfraToolKit. And what already the title says, it is all about combining visual programming languages together with the IFC schema development, and also see some benefits out of that. So to quickly motivate what has been done over the last years, so basically 10 or even 15 years ago, there was a clear demand or a lot of requests to buildingSMART, in general, the IFC world, to extend the IFC schema towards better support for infrastructure assets. Basically what has been done over the last years were several extension projects, starting with the IFC overall architecture and the IFC alignment project, which is just visualized here on the bottom of this left chart here, which has introduced which has led to the IFC 4x1 standard back then. Then next was the IFC bridge standard, which introduced certain new geometries and also really good semantics to describe bridge structures, and also specify certain components which are really specific to bridges. And after that, also the IFC rail, the road, and the ports and waterways projects have been placed and were carried out. And I assume most of you will know that we are currently have the voting process over the 4x3 standard, which is basically hopefully the next ISO certified one. Tunnel is also in the scope and is also running. I think there's also a parallel session right now. So basically what all these projects had in common were a rather similar structure on how they were managed. Basically, we always saw 2 phases, which will consist out of phase 1, where the domain requirements were captured and collected. Most of the times it was really not really data-driven, but more informal process, really to capture what is needed by the specific domain. And by producing the domain requirements reports, then the phase 2 was kicked off, and basically what happened in this phase 2 time spans was in most cases that a conceptual model was designed, and as an outcome we had something like an IFC extension, or more precisely a proposal on how to exchange the IFC schema in order to support that particular domain better. However, the problem of this layout was a bit that there was no real feedback loop on this initial setup. So the question was, how can we ensure that the IFC extensions produced by the technical experts really suits the requirements stated by the domain experts? So basically this feedback loop, just pointed in red, was not really in place, and that was also the motivation then to say in the infra room, okay, let's do a next follow-up project called the IFC infra deployment, and also similar in the IFC rail project. Basically, rail had a slightly different setup, but it was basically the IFC rail phase 2 project, where these projects have asked themselves, okay, we have the software vendors who are capable of understanding the extension, what we have defined so far. And we also have the domain experts which really know what they want to have in the IFC models, but how to bring these 2 worlds together. So now, considering also where I'm coming from, well, I'm based in a university. So a university is not really a software vendor, and we are also not really a domain expert, at least not what we are aiming for at our chair. So the question was, what can we do and how can we assist in that process? Basically, what we came up was like, okay, we need some kind of sample data, and actually the sample data in the beginning doesn't need to be really big or like contain huge like assets, but it's really about like showcasing and validating small concepts which were newly introduced by these schema extensions. So the question was really, how can we do like prototyping, and how can we do it in a way that we are quite flexible, and how can we act on like the continuous development process, which normally happens in these extension projects quite heavily. So the question what we've asked ourselves was really about like, how can we do this kind of prototyping and also being flexible? So basically we saw two options. The first option was to say, okay, let's stick with what we already had, like existing software, existing like vendors that already like provide certain IFC import and export capabilities. Just to name a few of them, which were partaking in the IFC road and the infra deployment project, but of course, needless to say, there are many more. So that would be like one option. Sometimes these interfaces are open source, sometimes they are closed. So that's already like a downside. However, as really contrary to that approach, which could be named as more like less like a black box one, where we have the single button option, is like we could explore certain programming frameworks for IFC data. So we already heard this morning or this afternoon, depending on the time span, that there is like the IfcInfraToolKit, there's something like IFC.js, there's the IFC Open Shell initiative, there's the ODA toolkit, and many more, which basically helps you to take the IFC schema extension, like serialized in an Express file, or even using the XMIs, whatever, and then to create like really programming code or classes or definitions out of that, and to then interact really using programming code, going into your like your environment, using Visual Studio and so on, and then really like hard coding examples could be the other option. So say we can say, okay, going to the right side, having these programming frameworks offers us some more flexibility. However, it's rather certain that you also do mistakes doing this kind of programming stuff, really, if the schemas or the concepts you're trying to test are not well described so far. So we are losing consistency if we come. So the resolution for that problem of this, like using existing tools versus doing everything from scratch using programming code, was a bit of a problem for us. So we thought, okay, how can we combine both worlds together? And basically what we came up with was the idea to say, okay, there is this concept of visual programming languages, and that's kind of adopted in the industry, also in the AEC domain. Where you basically have like a set or a library on your left or somewhere in your canvas, and then you have like a canvas where you can assign nodes and edges. Basically what you formulate here on your canvas is really like a data flow where you say, okay, you have certain nodes that have an output on the right side, you have other nodes that have an input on the right, on the left side, and basically each node visualized here on that canvas takes a specific job or helps you to like, perform your task, but having it in a kind of tangible way. So it's really easy to just decouple a node and like insert another value or reuse a value that was calculated in a former node, something like that. And yeah, basically you already know that. I mean, that's quite adopted quite well within the Autodesk products, but also in Grasshopper and Reno, and also Node-RED. And just to list certain use cases for this visual programming idea is like geometry processing, model filtering, and so on and so forth. So the idea was really to say, okay, how can we use these programming toolkits, which I was just showcasing in the previous slide, and how can we bring them into such an environment which ensures kind of like what we are doing. So we really encapsulate a certain piece of understanding into one node. And then we have like the user is a bit more safe in what he's doing because he doesn't need to do really coding, but there's still more flexibility instead of these single button solutions. So what we did is basically creating the IfcInfraToolKit, which was already in the title, using the schema documentation, using the express files, and also using Geometry Gym as a library. Thanks to John for that amazing support, which is also early binding or really up to date. And then basically create a plugin for the visual programming language Dynamo, which is also open source and has a really good support within a standalone version, which is called the Dynamo Sandbox, along with the Revit integration on the Autodesk side and also Civil 3D integration. So basically the idea was to have like a core implementation that works on all these Dynamo instances. And once you want to like really utilize Revit specific data like geometries, then you would go to that extension. Or if you have something like which is only supported in Civil 3D, like alignment data, for example, which is not really present in Revit so far, then you would directly jump into the Civil version. And you already see here on the canvas how this looks in a really simple example. So we have nodes where we can create a model or even open a model. And basically what we can do is then really compose the IFC file step by step. So we could say, okay, please add a facility, specify a name, specify like a host GeoID if you want to do like spatial nesting, something like that. You could add roads, you can also add facility parts, and of course you can also add components elements. So let's quickly look on a small example here. So we have a really easy or simple bridge here, just consisting out of several cuboids with 2 abutments and a deck. What happens here on the upper side is also creating the IFC model, or basically the basic skeleton of the semantic part. And at every time we can simply use such a watch node, which is currently inserted, to simply check the content which is currently present in the model. We see everything is fine. And what now happens within these green boxes is basically that we assign the geometry to the semantic products of the abutments and the decks. And last but not least, we insert a node which does the model saving. So just store the resulting IFC model we have just composed within our canvas to our disk, or so like locally. And we can also then directly go to BIM viewer, for example, BIM Vision in that case, and we see the model visualized here. And we also see on the upper right, which might be a little low, that we see like these 3 components together with the geometry. So that was a really simple example. That's where we have started our journey, so to say, because in the beginning it was really about like testing simple concepts and then extending step by step. However, we also extended that approach to also really do work together with the domain experts, as I was introducing in the first slides. So we used the storylines within the scope of the infra deployment project, where basically like domain experts has formulated a statement on, okay, we want to model that certain asset, and they've provided us with certain plans and drawings and also sometimes models. And with the help of Autodesk, which was like a co-partner for us as TOM in that project, we got models, and I used like the Revit integration of my tool then to assemble or to compose a slightly bigger dynamo graph or data flow to create also an IFC4X3 based bridge model out of that. And that's again visualized here in BIM Vision, quickly shown. And actually, this was really beneficial because we had really discussions together with the domain experts, and the domain experts said, okay, actually, it's not that nice how you, so myself, have modeled like the spatial breakdown, for example. So we don't want to have the road on a similar level as the bridge, for example. So it was just like a small refinement within our Dynamo graph to say, okay, please nest the spatial container of the road under the bridge or vice versa. So just not like discussing stuff on diagrams or using UML or really doing like high level stuff, which is also important, which is normally the language of implementers, but really to break it down and to say, okay, that's the model, you can navigate through it, you can visualize it using existing tools to a certain extent, of course, because we're dealing with new concepts which are not quite implemented in all the IFC viewers so far, but that was really a nice thing and really helps also the like domain experts, which are not like programmers, to understand what's going on and how like the new IFC extension models or IFC extensions can help them in their daily workflows. So to quickly sum it up, basically what we have done is this integration into the Dynamo to assemble IFC models. This approach has allowed us to do rapid prototyping and also sample data generation. The sample data are also published on the GitHub sites. I assume that was already topics in some former sessions this week or last week. We had intense discussions about how we can assemble these models and like really doing like conceptual work on not only having the class definitions or the entity definitions, but also like the first baby steps towards something which normally is known as an MVD or even concept templates where you say, okay, if you want to model like a bridge spatial breakdown, then you should assemble certain entities due to that this and that schema. So that was really the target of our models, and that turned out to be really beneficial and powerful in the end. Apart from that, we are also tested the approach for certain teaching activities here at the university, which is also quite good because we can really break down concepts now into these nodes, basically. So if we have a student or if we have a project where we want to extend our toolkit and we have like really specific requirements, for example, for geometry representations, we could say, okay, like semantic part is already done. We can generate even almost any products. We can assign property sets and so on and so forth. So please now focus on a new kind of geometry representations. Right now, we're doing a lot of BREP geometries. Or the next step could be to say, okay, here's the toolkit. Please implement a new node that only takes care of swept geometries or like extrusions. That's really good because then you don't need to understand like the overall architecture or the overall idea of IFC, but you can really say, okay, these are the few entities you need to implement this or that. So basically we were kind of successful. We had this feedback loop. And so we've kind of bridged the gap between the programming side and also the domain experts. And with this, I'd like to close my presentation, quickly acknowledge and to my student assistants, which helped me a lot with programming certain things. Also special thanks to Geometry Jim, John Merchant et al. And also the continuous support by Autodesk, which is like a long collaboration with the Leonhard Obermeier Center here at TUM. And last but not least, all the technical experts which were involved in the road project, in the rail project, and also in the infra deployment project. That was really a great honor to be with you in that team, and I wouldn't be that far if I have been part of that journey. And so that's all from my side. Thank you.
Thank you, Sebastian. That was really interesting. Some great progress with the work you've done there on the IfcInfraToolKit. Next up, we have a presentation from Peter O'Brien, and this is titled From Pixel to Pset, the Digital Structural Inspection. So over to you, Peter.
Good afternoon. My name is Peter O'Brien from VCE, Vienna Consulting Engineers. And on behalf of the project team, I'm very proud to present our buildingSMART 2021 award-winning project, From Pixel to Pset, once again here today. Our technology solution is a collaborative effort developed by the corporate startup StructInspect and VCE, Vienna Consulting Engineers. Both companies are based in Vienna, Austria. For the award submission, we chose to demonstrate our technology solution based on a project undertaken for the Autobahn GmbH, the Motorway Management Authority in Germany. The particular structure on which we demonstrated our solution was an infrastructure bridge on the A99 motorway ring around Munich. So I'll begin by providing a high-level overview of what our technology does and what inspired us to develop this idea. But first things first, our technology addresses the field of digital asset management and facilitates the digital structural inspection and maintenance management of concrete structures. Our overarching ambition is to optimize, automate, and ultimately make a digital structural inspection more accessible for the mass market. In turn, we aim to promote the wide-scale industry adoption of an openBIM-based structural inspection standard. The central component in our technology solution is the StructInspect platform, which enables a civil engineer in charge of a structural inspection to manage the entire lifecycle process. The platform is powered by an artificial intelligence-assisted damage detection procedure. Using only pixel images of the structure, the technology can detect, analyze, and classify damages according to the respective level of severity, dimensions, type, and any other attributes required to describe the damage. As part of the advanced inspection services, the platform also offers the provision of a digital twin in the form of a point cloud or textured 3D mesh model using photogrammetry. All of this can be managed through the StruckInspect platform throughout the entire lifecycle. And now, the provision of IFC and BCF capability enables infrastructure operators to interface with the entire openBIM universe. I come now to our process diagram in order to help explain all the procedures in our technology solution and to describe the journey from pixel to Pset. I've divided the entire process into 6 sub-processes: input data, digital inspection process, digital inspection output, BIM processes, BIM output, and federated BIM output. So beginning with the input data, the reason we decided to name our project Pixel to Pset is because as an input, all we require to begin the process is really only high-resolution pixel images of a structure. Such images are often taken using drones for larger structures where we encounter difficult terrain or in order to reduce or eliminate disruption to road or rail operation, as well as to reduce the costs associated with scaffolding and setting up platforms on site. The use of drones also helps avoid any risks associated with abseiling and working at height. However, terrestrial camera images can also be used for smaller structures. Typically, a 42 megapixel camera with a telescopic lens provides us with sufficient resolution to identify damages and create a digital twin. For the A99 project, a terrestrial camera was used instead of drones on account of the small size of the structure. So, based only on this input data, we have 2 primary operations that are performed as part of the digital inspection. The first is the creation of the digital twin. As part of the StruckInspect Advanced Inspection Services, a digital twin can be created using photogrammetry. The result of this process can be either a point cloud or a textured 3D mesh model, depending on the end user's requirements. However, either point cloud or textured model can be used equally well, as we'll see later when we describe the BIM processes. For the A99 project, we actually also had a terrestrial laser scan to assist us. But in this case, it was only because the Autobahn GmbH required a much larger site to be scanned than just the bridge itself, and therefore it was quicker to scan such a large area with a laser scanner. However, we also had the photogrammetric point cloud from the StruckInspect Advanced Inspection Services, and this would have performed equally well for the purposes described in this process. And now we come to the core function of the StruckInspect platform, and that's the artificial intelligence-assisted damage detection. This procedure processes the input images using neural networks with deep learning optimization to analyze discrete pixels in what is a highly sophisticated method that produces very detailed outputs. All defects are identified, analyzed, marked, documented, and classified according to the respective level of severity, dimensions, type, and any other attributes required to describe the damage. The process is trained to differentiate between many different damage types, the most common of which are cracks, spallings, and exposed reinforcement. One of the outputs of this process are segmented images showing the contours of the identified damages. In addition, all damage data such as type, size, classification, and severity are recorded. So 2 data sets are produced from the AI-assisted digital inspection. One contains numerous geo-referenced 3D points defining the contour polyline of the damage. And the other data set contains the damage attribute metadata. And this is all we need in order to produce our BIM damage models. And now we finally come to the BIM processes. In order to interface with the BIM world, we use the Python IFC OpenShell to transform the 2 data sets into highly detailed, information-rich IFC4 structural inspection models and BCF 2.1 structural damages reports. Elements representing the damage's shapes, sizes, and positions are created using IFC extruded area solid geometry, as we determine through trial and error that such extrusions maximize visibility in the BIM model and provide the optimal graphical impact. The damage attribute data is then stored on a user-defined Pset. At the time we submitted our technology in the buildingSMART 2021 International Awards, our tool existed only as a headless back-end function. However, we've since been developing a graphical user interface that will allow the end user to manage the creation of their own BIM models. The entire process, which will include their own attribute and entity mapping, and should be online in the coming months. It's worth pointing out also that the tool is more than just a straightforward IFC writer. It also undertakes several complex boundary curve optimization algorithms, numerical processes, and orthonormality checks required to prepare the raw data for BIM model generation. But unfortunately, I haven't got time to go into that detail in 20 minutes. So instead, we'll jump ahead and have a look at the IFC output prepared by our technology solution. And here you can see that we have only produced extrusions floating around in space. And this model is not particularly useful by itself, as one of the overarching goals of our technology is to be able to provide a clear graphical overview of the structural condition of the bridge, which means being able to show the relationship between the various damages and the context within which the damages have occurred. Therefore, we require a geometrical reference model of some kind to provide orientation and meaning to the structural damages model. So this raises the question from where this reference geometry should come, and luckily there are a few options. Now, some clients or projects require an information-rich as-built BIM model and others do not. In the case that an as-built BIM model is required, then a standard scan-to-BIM process can be undertaken, in which the point cloud is used as a reference on which a BIM model can be built manually using any off-the-shelf BIM modeling tools like Revit or ArchiCAD. Alternatively, the point cloud or textured model itself can be used as a geometrical reference, and to great effect also. And I'll now show how both of these alternatives can work. For the A99 project, our client, the Autobahn GmbH, chose to invest in a complete as-built BIM model. The elements shown here in red are the bridge structure and the acoustic wall. However, the entire area around the bridge was also of interest and modelled accordingly. The resulting scan-to-BIM model was produced using Revit and handed over in 33 separate IFC4 aspect models. To supplement the scan-to-BIM process, structural information from the original 1972 hand-drawn rebar drawings and subsequent inspection reports was also entered manually into the BIM model. So in this case, it was possible to use the resulting federated model to provide orientation and reference to our structural damages model. And here we can clearly see each damage as an extruded solid with exactly the correct location and size and all relevant structural damage information, including links to images and structural inspection reports. And this BIM model represents a self-contained single source of truth depicting the structural condition of a given structure at a given moment in time. And using our technology, all of this can be produced in an automated process based on simple pixel images. However, the other alternative to an as-built BIM model is to use either the point cloud or the 3D textured model prepared by the StructInspect process as a geometrical reference model. For the purpose of visualizing and understanding the damages model, this approach works equally well and actually has the distinct advantage of avoiding the expense and effort of the manual scan-to-BIM modeling process. And now that we've covered the model production, we can go back and look at the other product from our IFC OpenShell operation. So as a parallel process and based on exactly the same pixel input data, a VCF 2.1 damages catalog is created to accompany every IFC4 damages model. This report includes every damage identified at the time of the digital inspection, and using the VCF viewpoints, which are calculated numerically from the damage geometry coordinates, we can jump instantly to the respective damage. And thanks to the persistent and consistent GUID management system that we've implemented, we'll be able to track each damage throughout the entire life cycle. This BCF damages report can then be uploaded into any BCF server. Here we've uploaded into BIM Collab for demonstration purposes. We've implemented the BCF functionality in order to provide a mechanism by which information can be transported from the field directly back to the digital twin, thereby completing the digital round trip. This can be achieved using any tablet or head-mounted device. Here we see an example from the A99 of the HoloLens 2 in action. The device downloads the damage data directly from the StructInspect platform, and then using BCF issues, the inspection engineer can monitor the evolution of each damage during interim inspections. Since the buildingSMART 2021 awards, we've begun the process of integrating server-hosted BCF collaboration directly into the StructInspect platform. But until this is complete, we can continue to using any other BCF server, such as BIMCollab. And now we come to the last stop on the tour from Pixel to Pset, and that's the good old topic of 2D drawings. Put simply, 2D drawings are still required and will be required for some time yet. They're currently created manually with considerable effort, whereas our solution enables an efficient preparation of 2D drawings based on the IFC damages model superimposed over any geometrical model using an off-the-shelf BIM authoring software such as Revit or ArchiCAD. And what's more, the geometrical model can be either an as-built BIM model, a textured 3D model, or simply just a point cloud. And to demonstrate this, I'll now hide the BIM model in this example here. And so now we're only looking at the point cloud and our automatically generated IFC4 structural inspection model. And now if we're to view the two side by side, we see that even without a complete as-built BIM model in the background, our technology enables the efficient production of a high-quality 2D overview drawing. And now to demonstrate a few of the key use cases. The first main use case is to simply provide a better overview of the damages in any given structure, and more importantly, to help understand the relationships between the damages in a structure. Being able to display the damages with such clarity enables a civil engineer to more easily identify a potential connection between damages that may have otherwise appeared isolated or unrelated. In turn, this increases the chances that the correct mitigation measures can be identified, prescribed, and undertaken. The second immediate use case is to facilitate the BIM-based management and tracking of areas to be maintained. We have the ability using the StructInspect platform to draw areas manually on the images and enter any maintenance measures required for that particular damage. This sketch can then get mapped automatically onto the image surface, which in turn enables us to extract the coordinates and prepare an IFC and BCF model using exactly the same method described earlier. These models can then be used to track and manage maintenance costs, measures, and forecasts using any third-party control software, like i2, for instance. And the third obvious and immediate use case is simply the ability for a civil engineer to complete the digital round trip using BCF. Current industry practice sees this information stored in minor inspection reports or addenda, whereas our technology solution provides the transparency and accessibility of this information by enabling an engineer on site to enter comments and damage updates directly into a tablet or augmented reality headset and transfer the inspection update directly back to the BIM model via BCF server synchronization. So to summarize what it is we've achieved with this technology, we've succeeded in combining several highly innovative technologies, which has culminated in a number of powerful use cases for openBIM. We've already attracted considerable interest from infrastructure operators in Germany and Austria. And since the buildingSMART 2021 award submission, we've since begun providing services for an additional 2 infrastructure operators here in Austria, as well as a construction company. Our solution offers the asset management industry a ready-to-use practical solution to an immediate challenge. In turn, this helps guide the asset management industry's digital transformation in the direction of openBIM standards. We've lowered the commercial and knowledge investment costs associated with the digital transformation by providing a self-contained and largely automated solution, from pixel image through to complete BIM implementation. Our technology provides a civil engineer with a more complete overview of the structural condition of an object, as well as offering a method for the simplification of the creation of 2D drawings. Our technology provides all the ingredients required for a BIM-based cost calculation and management maintenance services across an entire infrastructure portfolio. And finally, via BCF, we have provided a site engineer the tools required to interact with a BIM model directly from the field, and thereby providing a mechanism for maintaining the BIM model in between the major periodic inspections. And as a closing statement, we've invited the Autobahn GmbH to say a few words from the perspective of an end user.
Für uns sind offene Standards, also die sogenannte openBIM-Methode, zwingende Voraussetzungen im Lebenszyklus der Bauwerke. Ganz einfach, weil wir nicht wissen, ob Softwareprodukte, die wir heute haben, in 10 Jahren noch am Markt sind und wie sich der Markt entwickeln wird und verändern wird. Also die diesmal eingesetzte Technologie wird uns momentan nicht unmittelbar einen Mehrwert bringen. Das ist immer so, wenn man in neue Technologien investiert, aber wir sehen langfristig auf jeden Fall einen erheblichen Mehrwert. Und zwar sehen wir ihn dort in der Präzision der Schadensdokumentation und in der Nachvollziehbarkeit und der Transparenz der Schadensveränderung über die Zeit. Die Auswirkungen auf die Branche möchte ich zweigeteilt sehen. Einmal unmittelbar auf die Bauwerksprüfung. Sie wird die Bauwerksprüfung ein Stück weit verändern. Sie wird die Schadenserfassung und Dokumentation wesentlich vereinfachen. Damit wird sich die Tätigkeit des Bauwerksprüfers wandeln und dadurch auch vereinfachen, hoffen wir. Und die Branche insgesamt wird davon profitieren, dass wir die Digitalisierung insgesamt vorantreiben und die Erfassung des Bauwerksbestandes und der Schäden ist der erste Schritt in dieser Richtung im Lebenszyklus eines Bauwerks. Für uns ist entscheidend die Dokumentation der Schäden über die Zeit und diese Nachvollziehbarkeit dieser Schäden eines harmlosen Schadens, der heute eben ganz unbedeutend ist, aber plötzlich in 10 oder 20 Jahren eine ganz andere Dimension hat und wir können dann den Schaden einwandfrei nachvollziehen, die Entstehungsgeschichte über den Lebenszyklus.
And of course, the project was a joint effort involving the skills of many others and in particular the vision and foresight of the client, the Autobahn GmbH. I'd like to take this opportunity to thank them all again. And so once again, on behalf of the project team, I would like to thank buildingSMART for all their proactive campaigning, for the openBIM digital transformation, and for providing us with a unique opportunity to showcase our application of openBIM standards and solutions on the international stage. We feel highly honoured to be named as the 2021 Technology category winners. The awards process really challenges us to perceive and assess our own technological achievements through the eyes of our peers and in turn provided us with a clarity and direction regarding the future development of our own technology. So for anybody still trying to decide whether or not to enter the buildingSMART 2022 awards, we strongly encourage you to do so because there's much to be gained from the process itself regardless of the outcome. So, thanks again.
The next one, which is openBIM, opening the gate of BIM and blockchain integration from Jinying Xu. So over to you, Jinying.
Thanks for the opportunity to introduce our works on openBIM. I'm Dr. Jinying Xu. We are a group of researchers from Faculty of Architecture, the University of Hong Kong. Our research is called OBI. It's about openBIM, which opens the gate for BIM and blockchain integration. From architects, engineers to contractors, from mass media, Harvard Business Review to Institute of Civil Engineers, the whole AEC community is talking about BIM and blockchain and the possible integration. Indeed, BIM and blockchain integration can enable numerous applications. For example, it can be used for global procurement, for supply chain status visualization, for material provenance tracking, and for smart contracts and smart payment. These are all particularly useful for our industry, which was traditionally well connected but now is isolated by the COVID-19 pandemic. BIM and blockchain integration can also be used for tractability, forensic investigation, and lifecycle management. However, there are several challenges for such integration. The first one is lack of interoperability between the existing commercial BIM software and blockchain. While people are excited about the potential, how to do that remains an issue. The second one is information redundancy. If directly storing BIM in blockchain, we did an experiment. We tried to put a PDF file of around 100 kilobytes into a blockchain with only 2 nodes. The total volume of the chain became 8 megabytes. This cannot be copied with when a BIM file around 1 gigabyte is consistently updated along its way. The third challenge is the resemblance and swiftness of retrieving the information from blockchain and restore to BIM. Ultimately, we need to restore the blockchain information back to a BIM for use. How to quickly do that and ensure the information is lossless remains a challenge. We found that openBIM, in particularly the IFC developed by buildingSMART International, provides a perfect opportunity for BIM and blockchain integration. Therefore, we formed a multidisciplinary team to tackle these fundamental challenges. The key point here is to restore and retrieve full BIM models on a blockchain using IFC files. As we know, Rome wasn't built in one day, so wasn't BIM files. No matter how big it is, BIM models are continuously growing along the whole project lifecycle. Both the geometric information and non-geometric information was designed, integrated, and used through the project, and the BIM model changes and evolve every day incrementally. There is no need to upload, change, and download full BIM models, which are very big, but we can just calculate the changes between gradually changed BIM models. Therefore, we developed this OBIS process map. From the up to the bottom of the process map, it shows how commercial BIM can be stored in a blockchain in an efficient manner. The topmost layer is the BIM users and the commercial BIM, and the second layer is the openBIM exchange layer. In the second layer, the commercial BIM files are converted into IFC versions and IFC formats so that we can calculate the semantic changes. In the third layer, the semantic layer, we applied the semantic differentiation transaction method we published in 2020, so-called SDT analysis, to process the differences of every day's version of IFC. And the fourth layer is the blockchain layer, where the information will be compressed, stored, and uploaded onto the blockchain with no information loss. And if one wants to have the latest BIM model at any time, they can use the upward arrows to have a reversed process from the bottom to the top. Then they can retrieve the BIM model from the accumulative SDTs. They can also import the IFC files into commercial software without the worry of information loss and long loading time. To realize the process map, we integrate the current BIM software ecosystem, which consists of different BIM commercial software and openBIM software, as well as our in-house developed apps for production inspection, transportation tracking, and installation supervision with the blockchain ecosystem, which includes the main interface, blockchain details, and smart contracts. We designed this 3-layered OBIS system as a bridge between the BIM blockchain consortium and the OB. The OB system with a particular web openBIM for users can visualize and track the changes. We have 3 layers in our OB solution: the web openBIM interface, the openBIM semantic interface, as known as the backend, and blockchain BIM as the data storage. Along with the project tools, we have many versions of the Revit, and we have the synchronized versions of the IFC. And then comparing every 2 versions of the IFC, we can have the SDT. And all these versions and changes are stored in the blocks on blockchain. And the commercial software like Revit, they can use the SDT ASONs and the node ASONs to read the semantic data as well as the blockchain data. In the WebBIM interface, the semantic changes can be updated and highlighted simultaneously in the 3D model so that you can locate and trace the semantic changes along the semantic hierarchy of the BIM project. This web interface can also help retrieve the semantic changes in the JSON file. And also, the block changes can also be viewed as the main interface of blockchain. The OB solution implementation also supports the current software apart from the user interface for users to read and visualize the changes. We also offer an API and ASON for the commercial BIM authorizing tools like Revit, Solibri, Navisworks, and also the construction management software like our in-house developed eInstar, eTranstar, eInstallStar for the concerned stakeholders to access data from the blockchain nodes, as well as to integrate the BIM changes as the SDT tree and the latest BIM.
We applied our solution to the HKU student residence project. This project is located at the Place Road, Huanzhou, Hong Kong. It involves 1,224 student places and supporting facilities such as canteen, common room, laundry room, and car park. Besides, it adopts modular integrated construction technology. When it comes to the implementation of our proposed solution, we use two buildingSMART tools, IfcInfraToolKit and IFC 2x3. We also used other software such as Autodesk Navisworks, Revit, BIM Vision, Hyperledger, and Solibri. On top of that, we also developed 3 in-house applications for off-site production, cross-border logistics, and on-site installation, respectively. So let's take a look at some examples. As you can see from this figure here, the inspector can record the measurement results of steel beam together with photos as a transaction in the blockchain system. The data structure of the transaction includes the name of the uploader, a timestamp, the IP address, and a hash value. Then the inspection statements can be uploaded in the BIM. Similarly, after the indoor works are completed, the quality inspection results can be recorded in the blockchain-based system, and then the results will be updated and reflected in the BIM. As another example, the inspection results of the furniture installations can also be recorded in the blockchain-based system and updated to the BIM. After the completion of off-site production, pre-finished modules will be wrapped up. Such state can also be recorded in the blockchain-based system and reflected through the BIM. Project participants can also check and view the transactions related to the loading and unloading of modules. Project participants can also check and view transportation of modules, thereby enhancing the just-in-time delivery. In the next step, we evaluated our proposed solution. The evaluation results show that, firstly, our solution has a high FC compression ratio, which means it can reduce information redundancy significantly. For example, the floor plan can have a compression ratio on chain around 1,500. Secondly, our solution offers lossless IFC encoding. Specifically, the block sizes were saved by 93 to 98% without losing information. For example, for whole building, the block size can be reduced from 2,551 in SDT JSON to 64.1 kilobytes using gzip B85 encoding. Thirdly, our solution provides rapid IFC restoration from blockchain. For example, the BIM models can be quickly restored with the retrieving a 160 MB SDT records to IfcInfraToolKit JSON file in 0.6 seconds. With the integration of openBIM and blockchain, our OB solution has three main innovations. The first and most important one is that LB tied up the IFC for BIM and blockchain integration. We don't need to store, transfer, and restore large BIM files, but just their changes between different versions using IFC. This relates to the second innovation. We invented an innovative and brilliant methodology to blockchain the changes by only calculating the semantic differences between IFC files. Most importantly, we can retrieve the information from blockchain of the semantic changes and restore the latest information to a comprehensive BIM model without time delay or information loss. To wrap up a bit, our BIM solution has three advantages. Firstly, we offer an intuitive and interactive visualization platform using openBIM and directly show every change of the BIM model so that stakeholders can track the model changes and check the authorships in a real-time manner. Secondly, our OB solution offers a high comprehension ratio of 800 to 1500 times to store the changes on blockchain, so that the very tricky information redundancy problem can be largely resolved. Lastly, but more importantly, our OB solution can quickly restore the BIM models from semantic changes. For example, for 160 MB of semantic differential transaction records, we can retrieve it to IFC JSON file in only 0.6 seconds. We believe that our solution will greatly contribute to the implementation of openBIM in practice because it can help solve the most burning issues of information redundancy and change tracking. In the future, we will work with the industry, buildingSMART International, and the health sector to fine-tune and promote our OB solution. In the near future, we will fine-tune the OB with a collaboration with designers, clients, and contractors to test, validate, and improve the solution in real-case applications. Meanwhile, we will seek support from the Hong Kong chapter of buildingSMART International and the Hong Kong Construction Industry Council to develop an IFC blockchain scheme and even standard. Actually, we have already secured great recognition and support from both organizations. They are very interested in our OB solution and are very willing to help us further develop and promote the solution. Finally, once the IFC blockchain standard is well developed, we will work with the buildingSMART international community to promote the OB solution in Hong Kong and the global, to better harness the value of openBIM in the AEC industry. Here are the key participants. We have Professor Wilson Lu, Dr. Frank Xue, Dr. Jinying Xu. Our special thanks go to our industry partners of the KIDS project, especially Mr. K.L. Tam from Hong Kong East Office and Mr. James Lee from Paul Y Engineering Group Limited. We can be contacted via wilsonlu@hku.hk. Thank you very much.
That was fascinating, really interesting, and I really like the work done, in combination with the Hong Kong chapter, which we know is a very strong chapter. So we probably will conclude early if there are no questions. Okay, well, with that, I think we will conclude the buildingSMART user conference. It's been a fantastic 2 days, and thank you to everyone that's made it happen. Thank you to all our speakers and all our attendees, and we look forward to seeing you at the next buildingSMART event. So thank you very much, everybody.